Good evening and welcome to the Marine and IMRAS Southern Joint Branch technical lecture on second generation intact stability theory. So before I introduce you to our speaker, I'd just like to do a bit of housekeeping to start with. So first of all, we have two types of attendees tonight. We have attendees and we have people that we added as panelists in order to increase the number of attendees. Could everyone who's a panelist please make sure that you mute your mic and turn your video off? That's great. I think most of you are muted. It's just so we don't get any feedback loops going from like videos and things like that. Secondly, we will be having a Q&A session at the end of the lecture. Now, if you look down at the bottom of the screen, you should see a little button called Q&A, and you'll be able to post your questions in this chat box. And at the end of the lecture, I will read them out and then Andy will answer them. You can choose to make your questions anonymous or not. It's entirely up to you. And so moving on then, I'll just like to introduce our speaker who is well-timed, you know, sharing his screen. So Andy, well, we actually went to university together, studied naval architecture at Newcastle University, graduated in 2007, I believe with a first-class degree with honours, and then went to Parametric for a couple of years before moving on to Global Maritime, and then ending up at Lloyd's Register, where Andy's now team lead for our stability load line and tonnage team here in Southampton. More importantly, more relevantly, Andy's been greatly involved at the IMO development of the second generation intact stability criteria, and I can't think of really a better person to explain what this all means to us. So without further ado, I'll hand you over to Andy.
Good evening everyone and welcome. Thank you for joining me for this presentation for the RENA and IMRS Southern Joint Branch. My name is Andy King. I've worked for Lloyd for the last 8 years, and as Lizzie mentioned, I'm now in charge of the stability load line and tonnage section, normally based in normal times in the office in Southampton, but obviously talking to you this evening from home. I should say for this presentation that the views expressed are my own. I'm speaking on behalf of myself and not on behalf of my employer Lloyd's, the MCA or indeed the IMO. And as Lizzie briefly mentioned, I'm here to talk to you this evening because I've been involved in this work for the last 7 years, representing both the MCA and Lloyd's at the IMO annually for the development of this criteria. And this year particularly, we've now reached a quite definitive line in the development, and we'll go through it. So the content of the presentation, I will talk you through the current stability criteria, what might be termed the first generation, and then what scant information there is currently for guidance for dynamic stability phenomena. And then I will look at where we've come with that into developing the second generation intact stability criteria. That criteria has got 5 key stability failure modes, and we'll go through those in turn. And then lastly, we'll look at where we are now, what's the way ahead, and then lastly, what does it all mean for you that are listening? That may be class, flag, industry, ship design, as well as the crew. I should mention that the purpose of the presentation is very much a high-level overview. So in introduction to the whole subject, I am not going to drill down to regulatory wording or the criteria or numbers. It's not that in-depth. It's much more high-level, the principles of the phenomena. And so the first generation stability criteria is very much what has come from the historical development of any form of stability criteria. That started with a gentleman called Rahola in the late 30s, and then moved through the 60s through to the development of what is the first set of defined stability criteria at the IMO. And the principles of this first generation criteria, the ones we are all as naval architects and other engineers familiar with, is that the water lines are level, there are no waves considered in the analysis, and because of that, the vessel is static, and this gives an unchanging righting lever, or GZ curve, that we'll all be familiar with. And then crucially, for a given loading condition, this means that the writing lever or a GZ curve is singular. There is only one. And if you would like a bit more information about the historical development of the criteria at the IMO and the development of what is now the IS code, then please take a look at the explanatory notes and the references on the slide. Hopefully you haven't missed any content, but I've just summarised the historical development of the first generation criteria. Now, crucially, what is excluded from that criteria is any form of dynamic behaviour of the ship in waves, the variation of the writing lever that comes from a ship in waves, and what is given is only simple textual guidance. There is nothing more substantive in the stability information booklet or any other guidance to the master on the vessel other than what takes up maybe a chapter or two in that booklet. The existing guidance can be found in Part A of the 2008 IS code, and it gives just precautionary provisions, some just high-level textual awareness of these phenomena. It gives the ambition for performance-orientated criteria, but none are given. So there are simple headings for writing lever variation, a resonant roll in a dead ship condition, broaching and other manoeuvring phenomena, but there is no substance to it, just a line that was written with the hope that those chapters would get filled in. Well, now they can with what is called the second generation stability criteria. So we've seen where it's come from over the last 70, 80 years, and to now where we are with the state of the art of the next generation of what's to come. So let's look now how it's been developed. The work has been ongoing at the IMO for several years, and I heard anecdotally that it's been one of the longest running agenda items at the IMO. It's been taken a substantial amount of work. It's been taken place originally in the SLF subcommittee, and now latterly what became the SDC subcommittee, the ship design and construction. And as you can see in the photo, that is taken at the IMO, that is the plenary session, where all the countries, the member states, and then the NGOs, the non-governmental organisations, that's where they sit and then debate and work out these kind of substantive items to do with criteria and regulations. So over that time, the criteria have been developed, and there has been a large number of sample ships that have been analysed, and that also includes a large variety of ship types. The draft criteria, as of now, have all been agreed, and we are currently undertaking the work that will finalise the explanatory notes. So a key point is to say that initially, this criteria will be non-mandatory. So it will feature in Part B of the 2008 IS code. And then it will be down to the flags that are in question for a particular vessel to choose whether it should become mandatory for a particular case. In terms of who has contributed to the work has been taking place in an intact stability working group, expert group, and then intersessionally, and by that I mean between the annual meetings of the IMO, which is generally around February time. So intersessionally, there is a big correspondence group where the intact stability experts can debate and refine things by email and by phone. The work, by its nature, has been highly academic, and this is because, as you might appreciate, we're trying to distill very dynamic stability phenomena into, in some cases, very simple binary pass-fail criteria. So on that basis, because of resource, computational ability, model testing ability, etc., it's been largely led by universities, and it's been principally led on that basis by Japan, the United States, Italy, and Germany. There's been valuable contributions from many other member states and NGOs, but for example, France, Sweden, IAX, and ITTC, to name many. And then the software development insights have largely come from the Finnish delegation, which has been most helpful. And then even other delegations, such as the UK, Norway, and others, have given practical views on implementation, on approval, on complexity, and contributing to that feedback process. So the format of the criteria is very well structured, and it's based on a tiered approach. There is 4 levels, and the 4th level is made up of 2 parts, so allow me to go through the 5 points. Level 1 is very much an initial simple check using prescribed criteria. It's very conservative, very much based on whole lines and speed. And if you allow it, it's something that you could do potentially on a spreadsheet. The level 2 criteria is moving forward. So if you fail level 1, you move forward to level 2. It's a more involved check, again using prescribed criteria, but is less conservative, and it's based on simplified dynamic computations. If a ship were to fail level 1 and level 2, then you would move on to what's called direct stability assessment, and that is much more involved, model tests, CFD and the like. And then there is operational measures, of which form up limitations and guidance. And that is such as, you would say, having been through all this process, you finally decided that a ship, for example, cannot sail in a given sea state or a heading, or it cannot do a particular voyage, but it also have then guidance then for the crew and anything specific for that vessel about when and how it can operate. This tiered approach is shown in this figure, and this figure is quite important because this has been taken from the current explanatory notes. So this figure will feature in the regulations when they are finally published. So you can see, moving into the diagram from the left-hand side, from the top, level 1 diamond, you can then pass or fail. And if you are not vulnerable to it, you can then confirm compliance. If you are vulnerable, i.e. you don't comply, you move downwards to level 2 and move downwards and so on as you pass or fail each mode. The key thing is, as a designer or as a consultant or whoever you may be, you can enter that left-hand side from any on any tier. You don't have to go through them in order. It's just that you can recognize as you go down the tiers, they require more computation, more time, more money, etc. So you might always start level 1 because it's the quickest, simplest, cheapest way of checking, and then moving down that system. And then obviously, if you fail all of them, then you can then go back along the bottom line to modify inputs, modify loading conditions, modify your design, and start the process again. So we'll move on. If the vulnerability criteria are not complied with, that are very much prescriptive, a criteria that we might think of it as pass or fail, if you do not comply with them, then you must move forward to the direct stability assessment method. This is largely a choice of model testing or numerical simulation, or it could be a combination of both. But it is key to say that it's much more complex, much more resource and time intensive than doing the binary pass or fail checks in level 1 and level 2. But the intention is very much to balance complexity against practicality, the latest technology that's available, the latest software that's available. And then the safety level that is achieved by passing or failing at this stage is all about a defined average stability failure rate. And the numbers and background to that are in the regulations. In those, I should say, guidance is very much then the requirements for how you do this work, the procedures that you would go through, and then also how you would validate your work as well. If you did not comply with the direct stability assessment, having been through the entire process, and it was not possible to modify your ship or modify your loading conditions, or modify any other parameters for compliance. You might then consider operational measures. As I mentioned, that is a blend of operational guidance and operational limitations. Limitations limit the operation in a given loading condition. And operational guidance is a set of instructions for the master such that you might have speed and headings that need to be avoided. The limitations may be on areas, on routes, or season, or significant wave heights that need to be avoided. But as you may appreciate, in real time on board the vessel, this requires detailed weather forecasting. It requires the wave information to be known, and it also requires careful consideration of how that is presented to the crew. Just one final point to note, when we come to the dead ship failure mode, which is about a vessel with no power, is that we can only apply operational limitations to such a case. When a ship has no power and loses steering and propulsion, then no amount of operational guidance in the first place may prevent a machinery failure from happening. So the substance of the criteria is considering 5 key stability failure modes. They are parametric roll, pure loss of stability, surf riding and broaching, dead ship condition, and excessive acceleration. We will look at each one in turn, what causes the phenomena to take place, and then where applicable, we will look for an example and a video of the phenomena in action. So let's take the first one, parametric roll, and look at the background to it. It's very much caused by a variation in the righting lever. And this is when the vessel cycles between being very stiff and being very tender as the waves pass along the vessel. It typically happens in following or quartering seas, and that's when the waves are coming from towards the bow or towards the stern quarter. Also typically when the wavelength is approximately equal to the ship length, and also when the encounter period for those waves are approximately equal to half the natural roll period of the vessel. This phenomena, like many of them, are very sensitive to hull form and lines, and vessels that are very full in the mid-body and very fine at the ends, such as passenger ships, container ships, are particularly prone to this phenomena. You can see in the image of a wave passing along the vessel, and you can see in the plots below how the waterline, the red dotted line, is the still waterline, but then the light blue line is that waterline as it traces the wave trough at amidships and then the wave crest at amidships. And as that wave passes, you can imagine that wave crest is going up and down, and that's what causes the cyclical changing of the righting lever. I should say these images, again, are all taken from the explanatory notes, so they're all images that you will no doubt see in the regulations when they come out. So let's look at an example of parametric roll in motion. This is a model test, and I will just jump forward and allow us to watch about 20 seconds of video. This is taken from YouTube, so it's publicly available, a row-packed model at the University of Finland. And you can see again, classically, a very, very full mid-body, very, very fine bow and fine stern. And you can see as those head seas are passing along the length of the vessel, the motion starts building up such that you get this natural roll building up that gets towards the end quite extreme. And that is parametric roll in a model testing environment. In a real world scenario, we may look to a vessel called the Pacific Sun. It was built in the mid-80s, just under 200 meters long. It was LR class at the time. And it's important to say that the loading condition that the vessel was in complied fully with the normal, the first generation, you might say, intact, as well as damage criteria. But in 2008, it was caught in a storm 200 miles off New Zealand, and it started healing to over 30 degrees, such that, and you can see the image at the bottom of the screen, that is shown at an angle of 30 degrees. You can see the pictures on the wall that are hanging vertically, that you see the angle the vessel got to. But in the accident report, it was confirmed that parametric roll could not be ruled out. It should also be stated there was also some other issues with the vessel in terms of fin stabilizer action and inaction, but the vessel has now been broken up. And if you're interested in reading more, then the reference at the bottom is for the MAIB report. Another real world example then of parametric roll is this container ship that was filmed from the bridge of another passing vessel. And you can see very quickly the vessel starts building up some very large motions. And then it's worth remembering again, thinking hull forms, thinking hull lines, again, very, very fine fore and aft and very full in the mid-body. And you can see the kind of heel angles that are being achieved in that situation. So moving on to the second phenomena. This is pure loss of stability. Very, very similar physics to the parametric roll, whereby the righting lever is changing when the vessel is supported on a wave crest. So in this image here, again, you can see how the waterline changes as the vessel passes through a wave. And when you have the wave crest at amidships in particular, you can see the graph on the right, the red dotted line, the calm water righting lever curve. When the wave crest is at amidships, the blue curve, the GZ curve, lowers. Therefore, you have less righting energy in the vessel. So as that vessel can get caught on a wave crest and get sustained on the wave crest, you may get a negative GM, and that's what can cause the pure loss of stability, and in the worst case, a capsize scenario where all stability is lost. So let's again look at this is a model testing example filmed in Osaka, Japan. Osaka University being quite key because the professor that works there that is the chair for this work. And you can see the vessel that gets caught on the wave crest, loses stability, and over she goes. A real-world example of this phenomena is a vessel called the Ariake, a 1995 RoPax vessel, 150 meters in length. She experienced, in some bad weather, a single large stern quartering wave. Again, hit exactly what was required for this phenomena, a wave length roughly equal to ship length, and then gave an initial 25-degree heel. And then it got hit, unfortunately, by a second wave, which then, with sustained heel angle, gave rise to cargo shifting. And eventually, you can see in the picture, a very heavy list to starboard and an eventual grounding. And because of this incident, the vessel was declared a total loss. And a bit like the last incident that had fin stabilizer issues, this vessel also had cargo securing issues. So important to state that the stability event was not the singular event in the cause of the accident. And again, in italics at the bottom, if you wish to find out more about this real world case, then please follow up the accident report online. The third failure mode is called surf riding and broaching. It's a highly dynamic event and is subtly different to pure loss of stability. It gets initiated in the same way that a vessel can get caught on a wave, but then the vessel gets sustained on the downward face of the wave, such that it is essentially surfing with that wave, hence the first part of the name. And then the broaching event happens, and that's when the vessel is unstable in yaw. There is no control over there is no control due to the flow direction on the rudder being reversed from the rotation within the wave. And then the vessel can broach sideways and lose stability and control. So to visualize this further, we will look at another exactly the same model test, same hull form, same model. And you'll see the vessel gets surfing with the wave. It gets caught on that downward wave crest, and then it broaches, loses control, and turns over. The fourth failure mode is called the dead ship condition. It's the simplest failure mode to visualize, but it was one of the most difficult to model for the criteria. It's largely been developed from the conventional wind criteria, and it means, as the name suggests, it's when the vessel is considered dead. It has no propulsion, it has no steering, so it essentially turns beam on to the wind and waves and starts reacting to that wind and wave action. So that's the failure mode. And it's important to state the work with the conventional wind criteria was so in depth that it's my view that it will eventually lead to a refinement, a development of what we think of as the conventional wind criteria. I do not have any examples of this, both real or model testing. So we'll move on to the fifth and final failure mode, which is excessive acceleration. Now, we will recognize that it's generally very good to have a low center of gravity for stability reasons, but having a low VCG can make a ship very stiff, and that stiffness can give rise to very rapid accelerations. And you can see in the image, it is very dependent on distance, because it implies as the ship moves, as you change position from deck level, let's say up to the bridge, as the vessel heels over, you are traveling a further distance. It gives rise to the interesting consideration for a naval architect that the vessel may have a maximum VCG, but there may also be a minimum VCG as well, such that you may be operating in more of a window rather than our conventional maximum kg curves. A real world example of this phenomena was on board the Chicago Express, a very large container ship. It was GL class and a German flag, and that's important to state because of this case, the German delegation at the IMO was very much the driver behind the inclusion of this failure mode in the criteria. She was just off Hong Kong when she was caught in heavy wind and swell, giving very high roll angles. She was hit by one single wave on the starboard side that gave a roll angle to 44 degrees. And the motions, the vessel was in a ballast condition, the motions were so extreme and so fast at the bridge level that everybody on the bridge, other than the helmsman, were knocked completely across the whole width of the bridge, unfortunately leading to one fatality. The master was very seriously injured and also 4 minor injuries. But just like we were saying, the vessel had a very large GM, a very low center of gravity. So again, it's about thinking about that window of operations where the VCG might sit. And again, you can find at the bottom the investigation report if you wish to find out more. So I'm just clicking forward, sorry. So those are the 5 failure modes. So let's think about where we are now and what's the way ahead with this criteria. The key point of this year, just before COVID hit us in February 2020, was that all the vulnerability criteria and all the draft guidelines for the criteria were agreed at IMO. That happened at SDC 7. And then also the draft guidelines were agreed for direct stability assessment, as well as the operational measures to cover limitations and guidance. The current version And it's important to say that in case you wish to have the regulatory text or the current version of it, is that reference there, SDC 7 Working Paper 6 from this year. That includes the most up-to-date set of criteria that will become the new circular. The current correspondence group is then now developing the explanatory notes, and then that will be considered SDC 8 next year for finalisation. The explanatory notes, I should say firstly, the guidelines are about 60 pages. The explanatory notes currently run to over 300 pages. So you can grasp the complexity, the background, and the explanations that go into the criteria and the various levels. The way ahead now is largely, like everything, has been interrupted by COVID. The intention pre-COVID was that the draft guidelines were going to get agreed at MSc 102. That was due to take place in May, but has now been postponed. Once that takes place, and then once it's been agreed, then it will be released to industry as a draft interim set of guidelines. The intention is very much to collect then experience from industry, from all parts of industry, for feedback, for refinement and tuning of the criteria. And this is because of two key points. One is that there is definitely some known logic issues with the tiered approach. As you remember from that tiered sequence diagram, if you fail one, then you move on and go to something that's less conservative. But it was observed in some sample ships that that logic did not apply, so that you could pass level 1 but fail level 2, which wasn't the right logic that needs to be followed. So that's why we need some feedback and refinement. There was also some issues with non-standard vessels, and in particular, you will see in the guidelines exclusions for some, such as those with low weather decks. And this is because we're modelling a wave crest on the side of the vessel with very low freeboard. The wave can broach that freeboard, and then the mathematics of the phenomena of the criteria starts to break down. Once it's all finalised, as I said, it will be in Part B of the 2008 IS code, so it will be non-mandatory at this stage. But flags may choose to make it mandatory, or for a particular case, designers, owners may choose to seek compliance. So people like ourselves at Lloyd's, we are seeking to undertake further validation work to really prepare ourselves for when this lands. So what does all this mean? What does it mean for class and flag first? Well, most importantly, it's a new criteria that needs to be applied. So we need to work and increasingly get used to it. We need to work with the flags on behalf of them for application of it, if they choose to make it mandatory otherwise. We think it will potentially land on the desk at Lloyd Register, for example, in 1 to 2 years. But it is a very complex criteria to be understood, as well as a complex criteria to be modelled. So that needs as well, for class and flags and others, some work to be done on procedures for processing those calculations, and particularly for appraising things like direct stability assessment, operational limitations, operational guidance. There are some real practical considerations to be had about how submissions on those items are received, appraised, and then ultimately approved. For the wider industry, for yourselves that are joining this presentation, for naval architects, there is the awareness to be had, and as I said, a very complex criteria. The key point for designers is that it requires inputs, the criteria requires inputs that may be unknown, especially at the early design stages. So there is some cyclical work that may need to be done as those inputs become known and refined. If it's not your strong background, then it may need some further understanding on hydrodynamics and ship motions, and hopefully this presentation has given an overview on that. There are certainly some further examples and schematics in the explanatory notes. And then there are some considerations of, we have a non-mandatory criteria, but will it be applied? I must state that doing this work, complying with this work, does not remove the obligation to comply with Part A of the code. That does not change the conventional, as we called it, the first generation criteria. But please, as designers or consultants or owners, as you may be, please pass on any feedback you have through your IMO delegation, whether that could be via Lloyd's or via your governmental body, such as the MCA. We, I should say, as Lloyd's, are collecting feedback that can get passed back through either avenue. So you may choose to give that feedback to us via the MCA, or you may choose to give it back through IACS for the NGO view. For the crew, it definitely has some implications. The overall aim is to offer an increased safety level, but there are considerations to be had over the practicality of it. There will be an increased training, awareness needed, but how is it monitored in real time? It requires more detailed weather forecasting, more detailed knowledge and forecasting of wave heights, and then decision making based on that. So it will definitely change or have implications for onboard stability computers or information, such that there will definitely be a danger of differing, limiting VCG information. And we talked already about how a VCG curve may have an upper and now a minimum limit, so a VCG band. But as you can see in the graph below, there were some sample calculations done by Denmark. You can see how there may be maximum VCG islands as well. So the vessel may have a particular loading and a particular kg height that has an island of non-compliance. And that's where the stability information and the passing on of that information to the crew will become much more important. Whether that's through the likes of computers or polar plots remains to be seen. So some wider and final considerations for ship design in general. These phenomena that we've talked about are very much based on ship form, but it's also important to remember, for the instance that we talked about, there were largely other contributing factors. But as designers and owners and operators, we should be thinking, if one level fails and if it's not met, then what? Do we move forward? Or as non-mandatory criteria, do we escape out of them and say we cannot comply? That's some questions and some conversations to be had. But we should bear in mind that this criteria could become mandatory in future. So we very much need to consider the whole picture of what it means for ship design and compliance. But some final thoughts from myself is we should be thinking, are vessels suffering systemic intact stability issues? In my view, they are not. We don't have ships falling over for intact stability reasons. So the first generation criteria, the work that's been done for 70, 80 years, something in that is correct. But we would appreciate, by doing this work, by adding on additional criteria, we are offering an increased safety level for ship design. But for example, some ship forms are the way they are for a number of other reasons. So would a container ship hull form change just because of compliance with this criteria? That remains to be seen. And we also are in 2020, so I will remind those unaware that there is SOLAS 2020, much more onerous, and it remains to be seen after some sample ship studies whether some smaller, particularly road pack ships, can both comply with the existing weather criteria, SOLAS 2020, and this new criteria as well. So there is a lot of work to be done. As it becomes public domain and the criteria are released, any feedback you have, we'd be more than welcome to receive it. So in summary for the presentation, I would like to just remind you, we've talked about where we've come from, in quotes, the first generation criteria, how we have only very basic dynamic stability guidance in the stability booklets, but using all where we've come from, we are now developing and have finalised the second generation criteria. It is based on a tiered approach and considers 5 failure modes. As soon as MSc 102 takes place at IMO, COVID allowing, then the expectation is it will get released as a draft interim circular. The explanatory notes will follow in 2021. And then lastly, to take away is that this work, the new regulations, will have implications for all of us, be that class or flag, industry, crew, and ship design in general. And lastly, I would like to just thank you for listening, for joining me this evening, and I'll hand back to Lizzie.
Thank you, Andy, for a very interesting lecture. So, I thought it would mute there. Can everyone hear me now? I hope you can.
Yeah, I can hear you. We can
When I
hear
move
you.
on to questions, brilliant. I don't quite know why I thought that. First question is, why are the new rules non-mandatory discretionary initially?
Sorry, Lizzie, could you repeat that? It broke up for a second. Sorry.
So the question is, why are these new requirements, why are they non-mandatory initially? Why not go straight for mandatory?
For 2 reasons. Firstly, they are seen as very much a set of criteria that need to be released, and we need to seek feedback on them to improve them. And then the second point is definitely known that they are not fully mature. So we talked about some of the logic issues, and I think it was certainly my personal view that we will be encountering far more issues making it mandatory when, in terms of development of them, they are still quite immature. I would say the potential for becoming mandatory certainly exists in the future, but we are a few years away from that.
Okay, moving on to the next question. Is there adequate software available to model the criteria assessments?
So Lloyd Register, our software of choice for plan approval, is NAPA. And NAPA was represented by the Finnish delegation, so was very much involved in the development of, or followed the development of the criteria. And I know for certain that NAPA has got this criteria coded up in the latest releases. I cannot speak for any other software, but if you have a software of choice at your employer, then I would certainly think about contacting them, see if they have it developed in a certain release, or if they are working on developing it for the future releases.
Okay, thank you. The next question is, how does this compare to Part A compliance? Are some ship types likely to find this significantly more onerous than Part A or SOLAS 20?
I'm just going to stop sharing my screen because it's causing it to slow down. Sorry, Lizzie, can you just repeat that question? It was a bit stuttery.
Yes. How does this compare to Part A compliance? Are some ship types likely to find this significantly more onerous than Part A or SOLAS 2020?
We mentioned at the end of the presentation, my feeling, or certainly my knowledge, is that some ships do struggle to comply with this criteria. And it's by nature of hull form, by nature of the loading condition, and as I mentioned, particular cases being the container ship, cruise ship type hull forms, as well as the small RoPax vessels, or vessels that had issues in the past, again, are shown to have issues with this compliance as well. On a case-by-case basis, how it tightens up the maximum BCG or indeed the minimum BCG, it would have to be, the calculations would have to be gone through for that particular case.
Okay, so the next question is, has the wider marine industry been involved or consulted in the development of the new criteria, or has it been mainly academic driven?
That's a very good question. I think when I joined the development of it, it was very much academic. And I held a long-standing personal view that it needed more industry and more flag and more sort of practical application involvement. So a number of delegations got together to try to bring that. Everything from where the vessels are having intact stability issues in the first place, through to, and that goes back to whether you make it mandatory, can vessels comply with it, and what happens if they cannot? Lastly, and it comes down to the day job at Lloyd Register, is how you physically approve. It's one thing approving a level 1 and level 2 vulnerability criteria. That is a binary pass or fail calculation or set of calculations which can be repeated. But a direct stability assessment, a model test report, operational limitations or guidance, there is some substantial conversations to be had between class and flag about how that is formally approved. Because a client or designer or so forth may pay to do one package of work, then it will be a substantial cost to then have class repeat it and approve it. So that conversation definitely needs to be had. And I should just, one last, again, a personal comment is that we approved stability information daily at Lloyd Register, and it was interesting seeing a difference of opinion, even wording of things like validation, verification, appraisal, approval, and it was ourselves as class or member states as flags who were very, very clear about what the word approval means in a statutory sense, as opposed to, if I may say, some of the universities that were represented that were talking about validation and verification from a software point of view. So even the wording about how you check this stuff was quite key.
Okay, thank you. Then we have one more question, which is, has LR performed simulations of all 5 cases?
We have performed calculations for 4 of them. This was pre the final one that was developed, which now escapes me, being dead ship or surf riding. But yes, we run the calculations through NAPA. As a UK delegation, as well as my colleagues and others have also run their own calculations. I should just say, yeah, lastly, that is only through NAPA, so I cannot speak for software capabilities.
Okay, thank you. Well, that was the last of the questions. So I'll take the opportunity to thank you again, Andy, for a very interesting lecture. We shall certainly tap you for stability lectures in the future.
Yeah, I should say, if you do want any further information, then please get in touch with us at Lloyd Register. Thank you.
Thank you again. So just a couple of announcements for the end of the lecture. Firstly, if you have any feedback about this lecture, or any of our other ones for that matter, in terms of how it's gone, because this is only the second time we've run a Zoom lecture and we still have some teething issues, please contact us at TechSec, that's TECHSEC, at southernjointbranch.co.uk. This lecture has actually been recorded, so we will be posting it on our YouTube channel once I slightly edit the recording a little bit. But there'll also a link should be sent around to that by either Rena or IMRS, whichever you're a member of. And please follow our YouTube channel, and then you'll get a direct notification. For any of you who aren't already following us on Eventbrite, please do so, because again, you'll get a notification as soon as we publish our event on Eventbrite. You don't then have to wait for IMRS and Rena to send you an email. Our next lecture is going to be on the 10th of December, and that will actually quite a connected lecture, it'll be on the mitigation of surf riding and broaching events for small pilot vessels. So we've gone from the big ships down to the little ones. So quite a good follow-on for that. So with again, thank you, Andy, and thank you all for your attendance and for your attention. And hopefully we'll be back here in December.
Thanks all. Yeah, very good. Most enjoyable.